I'm the North American Program Scientist for ALMA, and I'm going to tell you about the ALMA status and vision for ALMA for the 2030s. So the picture I'm showing you, I chose it specifically for tonight's talk. It really demonstrates both how remote, dry, and isolated our site is at 5,000 meters, and also might help to explain why we had a fair amount of difficulty coping with the COVID-19 pandemic. In fact, we had to completely shut down the site for the first time that we've ever had to shut down for a really extended period, from about the 20th of March to October 1st, 2020. We were able to start science observing again for cycle 7, starting about the 17th of March, 2021. So almost exactly a year from the time that we had to shut down. It was a gradual startup with limited staff at the site because of the rigorous COVID protocols. We're very proud to say that no lateral spread of COVID happened at the ALMA site so far due to the rigorous protocols. Many issues were encountered and solved from the lengthy shutdown for over a year at this very challenging site. I put a link there that you can get to earlier, later on, that shows a really cool documentary of the observatory coming back to life if you're interested. Right now, the staff count is still limited to about 105 people, which is still well below the normal level. But this does allow critical maintenance and array configurations in principle, but unfortunately, we've been pretty unlucky lately with snowstorm after snowstorm. So they dig out from one snowstorm and then there's another snowstorm coming in right behind it. So we are pretty behind on moving to configuration 7, which is a shame because otherwise we were on track to be where we wanted to be to complete cycle 7. It's not clear yet how we're going to adapt to all of these weather issues. And also the pandemic remains a problem in Chile. There's still quite high case counts. And so there's still a more or less constant risk to ALMA operations, but hopefully everything continues as it has been. We did manage to have a very successful call for cycle 8. The review panels for medium and large programs are actually meeting this week. This was the first call that we had with distributed peer review for small proposals. The distributed peer review means that each PI that submitted a proposal had to themselves review 10 proposals. And it's been a pretty interesting process, and we think it's going to work well. We also are doing dual anonymous review now so that there's no identifying information of who the proposal is from in the proposal at all, which we think will help with some of the biases. It was a record oversubscription with more than 1,700 proposals, and the 12-meter array was oversubscribed in time by a factor of 6.1. So ALMA is embarking on a major upgrade to a wider bandwidth digital system with a goal of reaching at least 2 times the current system bandwidth and increased spectral sensitivity by 2030. And that's what I'm going to focus the rest of this talk on. So just to give a little bit of background first, the ALMA development program is in principle a $13 million a year program spread across the ALMA partnership. However, the actual management of this program is fairly complex because of the nature of the executives and the partnerships, we do not pool that money and spend it. Each executive has its own process, but the projects that get built have to be agreed across the full partnership. So we've already had a lot of successes with our development program, focusing on the obvious shortcomings of ALMA, in particular things that had to be de-scoped during the original construction or that in some ways aid science throughput. So for example, solar capabilities, the building of the band 5 receiver, and of course, VLBI, which enabled the now famous image of the shadow of the black hole in M87. But after those initial projects were done, it was pretty clear that we needed to come up with a solid plan for how we wanted to move forward for future development. And our roadmap, as we call it, it's called the ALMA Development Roadmap, is in Memo 612. The first thing that happened is that 3 new key science goals were identified: the origins of galaxies, the origins of chemical complexity in the universe, and the origins of planets. And what you find is that in order to accomplish these key new science goals, you need to enhance ALMA's observing capabilities. We need better continuum sensitivity, for which we need increased bandwidth and improved system sensitivity. We need increased spectral line sensitivity, for which we need improved system sensitivity and collecting area. We need instantaneous spectral range and tuning flexibility, which also requires increased bandwidth and a flexible correlator and angular resolution, longer baselines and more collecting area. So we have that brightness sensitivity at the longer baselines. So I've underlined increased bandwidth and system sensitivity occurs in almost all of these required upgrades. And so that was identified as our highest priority. And in fact, our highest priority for the next 5 to 10 years, as I'll demonstrate, work is well underway. We want to improve the receiver sensitivity. Currently, all of our receivers are within the 4 to 10 times quantum limit, but there is some work that can be done to improve them. We want to increase the correlated bandwidth by at least a factor of 2, which requires an upgrade to the whole digital system. We also have a priority to improve the usability of the science archive. And in the next decade, in the 2030s, we hope to extend the baselines by a factor of 2 to 3, increase the collecting area with more antennas, look into focal plane arrays, and perhaps build a 25-meter class single dish. So these items that I've highlighted in green, as I mentioned, require a major upgrade to the whole ALMA digital system, which at this point is about 20 years old. This is going to be a coordinated effort across the whole ARMOR partnership, leveraging our existing ALMA development program. And we have a goal for achieving this wideband upgrade by 2030, and will be the focus of the rest of my talk. There are a wide diversity of efforts underway across the partnership to improve the science archive, but I won't talk about them more today. And these longer term items are things that we have studies underway because they need research and development in this decade to try and make them a reality for the next decade. So there's been a lot of work in the last year and a half to specify the new requirements for this wideband 2030 digital upgrade. There are links that you can find in the talk later that will take you to these full documents. We've also had a series of community workshops, which are listed there. And the upcoming workshop, which will be virtual in Germany coming up in September, you can still register for if you're interested in receivers and front ends. Though I note that the website seemed not to be working earlier today. So if you find that to be true, you might want to check back in a couple of days. I've alerted them that it's not working. So if you don't want to actually look at all of these specification documents and the websites, this is a very brief summary of what they say. We want at least, as I said, 2 times increase in correlated bandwidth so that we get at least a square root of 2 better continuum sensitivity. We think that we can improve the digital sensitivity by at least 13%, which will improve all projects. And there are receiver sensitivity improvements. The second generation correlator will be of an FX, actually it'll be FFX architecture. It should handle both 7-meter and 12-meter interferometric data. We plan for it to be located at the OSF instead of the AOS at 3,000 meters, where it will be much easier to maintain and require a lower cooling cost. It'll have vastly more channels and will remove the need to give up bandwidth for spectral resolution. So this is showing you what the performance is in system temperature as though it were a single sideband receiver for all of the current ALMA bands, bands 3 through 10. And the lower dashed line is the 4 times quantum limit, and the upper dashed line is 10 times the quantum limit. Basically, anything that's above the 4 times quantum limit but below about 400 gigahertz can be improved. And in particular, some of these poor performance across the RF of these receivers can be improved. And then you have our double sideband receivers, which are dominated by the sky, but also these curvatures and poor performance at the edges can definitely be improved. So the first efforts underway are to fill the gaps. So there was a gap down here for bands 1 and 2. East Asia has a project underway to build what we call our band 1 receiver. It's from 35 to 50 gigahertz. It has an IF bandwidth of 4 to 12 gigahertz at single sideband. It has comparable or better point source sensitivity to the JVLA currently, especially on the high end. It's notably better in its frequency range, but it's in the south, so it's highly complementary. The status is quite a few cartridges are in Chile awaiting installation, and the goal is for PI Science to start in cycle 10. And it's a collaboration with North America and the University of Chile. I just note that band 1 is particularly important for a lot of reasons, but I chose this high redshift example just to show that over the epoch of reionization, you get CO 4 to 3 throughout that full range, or CO 6 to 5. Also of interest is that you can observe CO 1 to 0 at cosmic noon. That's the peak of star formation in the universe, which is of particular interest to really understand how galaxy evolution proceeded. The second gap is band 2, and this is an example of what band 2 would look like. The purple and the yellow regions are showing that at their goal IF bandwidth of 4 to 18 gigahertz, they could cover this whole band, which includes most of band 3 as well as band 2, in just 2 tunings. This project is approved for prototype and pre-production, and we expect to have a full manufacturing readiness review sometime early next year. This is a collaboration with East Asia for the OMTs and optics. So both of these projects are on the path for sure to hopefully be completed by 2030. In North America, we have been supporting several studies in support of the band 6 version 2. It has an RF range of 211 to 280 is the goal, which extends it so that you can pick up 13CS and N2H+ in the band 6. Right now, those lines are accessible from band 7, but now they'll be accessible also at band 6. The goal is to have IF range of 4 to 20 and definitely 4 to 16. It will have improved receiver temperature, especially outside the currently quite good 6 to 10 gigahertz IF range. And this will in particular enable much more sensitive 12 and 13 CO simultaneous observations, which really suffer right now from being at the edge of the current IF. You'll have access to more diagnostic lines and improved gain variation. I'll just note that band 6 is ALMA's most popular band. 43% of cycle 8 proposals requested this band, and 53% of all publications to date include band 6 data. Studies are also underway for many of the other ALMA bands, including bands 7, 8, and 9. A few highlights from the key second generation correlator. What I've done is color code these minimum requirements and stretch goals by how likely or challenging they are. Getting up to 80 antennas seems like it's going to be no trouble at all. This gives us some room to expand our collecting area with our current correlator, and it would be expandable in antenna space so that if we get the opportunity to build even more collecting area, we would be able to expand the correlator to match. Doubling our current correlated bandwidth looks like it would be well within our capabilities, but making it expandable so we could get to our ultimate goal of 4 times the current bandwidth. 4 times current bandwidth is quite challenging for a number of reasons. One of them is that right at the moment, the different correlator designs that we're aware of would max out our power. And that's a bit of a operations problem. And also, of course, the downstream subsystems like the archive and data reduction would also really struggle with 4 times. So right now we're thinking we would probably going to go for the 2 times, but then in a staged way, expand it later. It looks like 6-bit correlation is no problem to give us that extra bit of system sensitivity. And we're going to be able to do about 0.2 kilometers per second at least at 35 gigahertz at full correlated bandwidth. The best spectral resolution will be 10 meters per second at 35 gigahertz. And that also looks like it will be easy to achieve. And we'll be able to do that best finest spectral resolution with a bandwidth of about 1.6 gigahertz. So just some quick science examples. We assume a system sensitivity of 96%, which is about 13.2% better than what we currently have. This is actually equivalent to adding 6 more antennas to a 47 antenna array. This is just an example, the picture of an ALMA large program from FANGS. These are observations of 81 galaxies within a distance of 20 megaparsecs, which took 177 hours of 12-meter array time. After the digital upgrade, this would have only taken 138 hours. And here I haven't attempted to include any front-end improvements. To put that in perspective, that digital sensitivity improvement alone would be equivalent to about 1,000 extra hours of observing time per year. So 28% more observing time on the 12-meter array. So it's significant. What we'll also be able to do is cover spectral space much more efficiently. Here is an example from the PILS band 7 spectral scan towards a protostar. The blue is showing the detected line emission, and they observe all of the current band 7. And in order to get the spectral resolution that this project needed, they could only cover this red area. After the 2 times bandwidth upgrade with many more channels available, we'll have both of these black line regions. In other words, they would have been able to cover band 7 with 2 tunings instead of 18. We estimate that about 30% of the cycle 5 projects actually had to give up bandwidth for spectral resolution in the way that this project did. So it'll be quite transformational for astrochemistry and redshift searches. The wider bandwidth will also enable really what new continuum science in the faint regime. Sorry, what, Jim?
2 minutes left.
On the left, you see images of the D-sharp disks. And on the right, what you're seeing are state-of-the-art attempts to detect the dusty disks around the planets themselves, CDPs. And this project, which is really considered state-of-the-art right now, was marginally unsuccessful. And what I mean by that is they found some blips, which you see in these images, none of which are more than 5 sigma. But because of the difficulty in removing the underlying disk structure, they were not confident that any of these are real. The combined upgrades that I've told you about today would take those 5 sigma blips to 9 sigma detections. And so it really gives you the sense of opening up this new faint continuum regime. We in North America just had a big call for development projects. That process is just winding down. It looks like we're probably going to move forward 2 large and 1 small project. More information will be forthcoming about this in the coming weeks. This is just the first stage, though. I emphasize the next stage is for these projects to go before the full ALMA partnership and eventually the ALMA board. So later this year and by spring next year, we should know the outcome of these development projects. And just to note that we're hoping to have a call for studies, which are smaller seed projects, in Q2 of 2022. So thank you for your attention.
Okay, thank you, Crystal. Let me ask you the first question. Many observatories find that their weather is never as good as it was when they did the original site testing. How has it been for the ALMA site?
It depends on the year. We have had exceptionally good years. We have had exceptionally bad years. And in hindsight, compared to the site testing, we think it has a lot to do with El Nino and El Nina cycle. And that El Nino and El Nina control a lot of how much moisture comes up the backside from the Amazon over the Andes over onto the ALMA site. So we think we understand why we were sort of fooled by the weather, but we do also have really good years that are similar to the site testing.
If you're so vastly oversubscribed, why are you giving importance to filling in the spectral gaps? Maybe you should just worry about increasing the sensitivity, like prioritizing the more capable correlator.
Well, that's an excellent question, Jim, but I'm not sure that we have time to go into it. I will say there is critical and key science, especially band 2 is a wavelength regime that very few telescopes have ever covered. And there's a huge number of, for example, biologically interesting lines and so forth in that band. You can ask Eric Murphy to tell you all about it because it forms the key science case for NGBLA. So these bands were always in the ALMA science vision. And so it's been considered important to complete that vision before we move on.
Okay, thanks.